Okay, so chapter 6, section 5 is using proportionality theorem. So remember when we talk about proportionality, we're talking about that we have a whole bunch of fractions that are all equal to each other, like 4/8, 5/10, and 1/2. We're looking for things to be proportional, that they have that same scale factor. If you were to simplify all of these, they're all 1/2. So remember, we've done that before. We looked for all the angles to be congruent and all the sides to be proportional. Well, now we're going to learn some more things about proportionality. So we're going to go through and just talk mainly about setting up proportions and some things that we know using some new proportionality theorems. Okay, so the first one is the triangle proportionality theorem, and this is just for triangles. It says, if a line parallel to one side of a triangle intersects the other two sides. So what we mean here is that we're saying is if this line EB, if we know that it's parallel, we have to know that it's parallel. We can't just guess at it. If we know that it's parallel to DC, then it divides up the two sides proportionally. And what we mean is that that EB there is, it's running through and like running directly into those sides at those points right there. I'm going to blow it up a little. It's running directly into those points. So if you think about it, these sides are being broken and chopped up into two pieces on the left and two pieces on the right, because that point there has now broken them up. It does not mean that they are necessarily congruent. It could be that they are, but it does not mean that. It just means that they are broken up proportionally, meaning AB over BC, that is the right-hand side over the right-hand side. We're looking at this piece here. Here is AB. AB over BC, that's this right here, will be equal to AE over ED. Then we can set up proportions there. So if we know some information, then we can go, oh, okay, I know how to set these up. For example, if I've got 3 over 4, or 3 and 4 there, and I've got, I'm just making up some numbers here, 8 and x. So what we can do with this is that if we are looking for some information there, we can set up some proportions. For example, 3 over 4 would be equal to x over 8, in which case 4x is equal to 24, in which case x is equal to 6. So we could figure out that AE was 6. If we wanted to, we could figure out how long this whole side is there, because we know that one piece is 6 and the other piece is 8. So we have a lot of information that we can find out. But it only works because those two lines were parallel. If the lines are parallel, then it is a guarantee that the sides are being broken up proportionally. And that's the triangle proportionality theorem. Parallel lines break the sides of the triangle up proportionally. Here is the converse of that same exact one. Remember, there's the triangle proportionality theorem. This is the converse. So the first one said, if the lines are parallel, then the sides are broken up proportionally. Now we're going to say, if a line divides two sides of a triangle proportionally, meaning if like I look at EB here and I go, oh, hey, I see that these sides have been broken up proportionally, like this. And we see that 3/4 is equal to 6/8. Well, 6/8 is a fraction that reduces to 3/4. If we can see that those sides are broken up proportionally, well, then it is a guarantee that this line must be parallel to that third side, the side that it's not touching. So if you look at those numbers there and you can verify that they have been broken up proportionally, well, then it is true that EB is parallel to that third side. Now, I just made those numbers up. I didn't get those anywhere. I was just trying to illustrate how this works. Those numbers weren't anywhere here, but you will get to work with those numbers when you start doing the problems. All right, so let's try one here. So the first thing to notice is that we've got a triangle and we've got some parallel lines. That is the most important. A lot of people get into this whole congruent thing and start marking things as congruent. Nothing here is shown as congruent, but I do see that this line here is parallel to this line here. Now, what we just learned from the triangle proportionality theorem is that this one is breaking the triangles up proportionally. So that CD over DA is equal to what other fraction? Yes, ma'am. CE over EB. Sorry, that's a B. Notice we've got bottom right over top right is equal to bottom left, follow the same pattern over here, over top left. And now we're going to go ahead and use some of the numbers here. If CD is 3, let's do this in red for this one. So if CD is 3, DA is 6, DE is 3.5, then AB. So we've got this same situation here. So what we do is that while the sides are being broken up proportionally, one thing to note is that the bottom will also have that same exact proportion as well, is that we've got the exact same proportion going on. Now, here's the thing. So what we're going to do is we're going to also set up a proportion between this line and this line. And sometimes people are like, wait, why are those two proportional? Because isn't it the left and right? Yes, it is. But also remember, in situations where we've got like this is an angle of the small triangle, and it is an angle of the big triangle. Would you agree that there's a large triangle and a small triangle there, and that is an angle of both of them? And then additionally, since we have parallel lines, we could have corresponding angles right there, which would make these, you could go, oh, okay, well, since I've got angle, angle, these two triangles must be similar, therefore their sides must be proportional. So here's what we're going to look at. CD is 3. DA is 6. So CD is part of the small triangle, and 6 is part of the large triangle. Okay, so where we were looking at here is we were looking at the sides being proportional so that we can solve those sides by setting up proportions. But what we're looking at here is two separate triangles. Like if you can see them, there's a large triangle, which is here. Here's the large triangle. And here is the smaller triangle here. So what we're going to do is we're going to set up proportions. Now remember that when we set up these proportions, those lines will definitely break up the sides, like 3 to 6 right there. But when we're comparing two triangles here, this is the whole bottom of the big triangle, and this is the whole bottom of this. I say bottom, we can call it top if you want. We're just used to like that, like a triangle being pointy on top, so I guess I shouldn't call it bottom if it's actually on the top. So what I'm going to do is this. Now, if you look at the, I'm going to see if I can rotate this. Hang on a minute. Let's rotate it like this for a moment. So here are the numbers we were just given, that this was 3 and this was 6. And this right here, I'm just going to flip that over, was 3.5. So when we do the left-hand side of the small triangle, it is 3 units long. How long is the left-hand side of the big triangle? It's 9 units long. The reason that I'm doing the whole side there is because this is the whole bottom of the big triangle and it has not been broken up. So we've got the small left-hand side over the big left-hand side. Now we're going to do the small bottom, which is 3.5, over the big bottom, which we don't know, is x. So let's go through and, yes, ma'am?
I still don't understand why you're doing the whole thing.
Well, because, so we said, let me flip it back over here for a minute. We said that when we do it, it breaks up the sides proportionally, yes? So we could do, like, it was very easy to figure out 3 over 6, like, that these are in a proportion to each other. Like, these two numbers, we were able to set up a proportion with them. But it didn't say anything about this other side there, the third side. It only talked about the side that's being cut by this line right here. This line is cutting those two sides right there, but it's not cutting the bottoms. Like, when I say the bottoms, that other third side there, the parallel line is not being cut. So what we have to do there is we look at it like two triangles there. We've got 3 over 9 is equal to, that's the left-hand side of the small triangle over the left-hand side of the large triangle. The bottom of the small triangle, here's small again, here's small triangle, small bottom over big bottom. So we're going to cross multiply, and we get 3x is equal to 3.5 times 9. And what's 3.5 times 9? I got 31.5 as well.
Wait, can't you simplify? Like, why aren't you simplifying 3 over 9 just to make it easier?
Yeah, we could do that. She's saying, why not take these fractions and simplify them to 1/3? Sure, let's go back and do that. Here, let me go back and... So back here, she's saying, why not take that 3/9 and make it 1/3? Sure. So we get x is equal to 3 times 3.5, which gives me 10.5. So that bottom right there would be 10.5. Now notice it's not the parallel lines that are being broken up proportionally. So we had to do something a little bit different with them. I'm going to flip this over now because I just wanted to show it like that. I feel like people do better with triangles like that. So right now we know that AB was 10.5. We got that. Okay, so now we're going to change some things here. CB is, let me just redraw this triangle if that's okay. I'm going to redraw it, and I'm going to redraw it the other way. So C, D, A, E, B. I'm just flipping it over. I'm just flipping it over in my mind so that I can redo it again, and I don't want all my numbers mixed up here. So CB, the whole right-hand triangle here, is 12. EB is 8. CD is 6. And we're trying to find out what DA is, this piece over here. Yes, ma'am?
So you're going to set it up as 12 over 4?
12.
Because 8 minus, at least this is how I would do it. You do 12 minus 8 to find CE.
Okay, so she's looking for this piece right here, and she says the whole thing is 12, and this piece by itself is 8, meaning that this must be 4.
Yeah, so...
Actually, that's the last place that is the last time that I would actually use the 12. I would do the same as you. I would do that same first step, but I noticed that you're looking to use that same 12 again. I wouldn't. You could, but you don't have to. There's an easier way to do this.
Oh, because the sides are proportional.
Yes. So, well, right now that we're going to say, since, I forgot to draw on that these lines are parallel. We know that they're parallel, sorry. We know that in the picture as well. So she just said right there, we know that these lines are parallel, therefore the left side and the right side are broken up proportionally. So let's set up some fractions, some smaller fractions, which would be way easier.
4 over 6.
So look at the sides that are broken up here.
4 over 8.
4 over 8 is equal to?
6 over x.
6 over x. And tell me what you did last time, which you should totally do again.
Simplify it to 1/2 equals 6 over x. So then x is equal to 12. Or dA is equal to 12.
Yep. And what if I asked you how much CA was?
Then you would do 12 plus 6.
Which would give me?
18.
18. So no matter what I ask you for there, it's just a matter of using the proportions to solve them. But DA in this case was 12. So when we've got those parallel those parallel lines, they break up those sides proportionally. When it came to that third side there, that one had not been broken up proportionally, but we know that the bottom of the small triangle and the bottom of the big triangle, those will be proportional to each other as well. Left side of the little triangle, left side of the big triangle, right side of the little triangle, right side of the big triangle, those will all be proportional as well. So we can set up proportions that we know are true. Okay, so now we're going to use that same thing here, but we're going to use it using shapes that aren't triangles. If three parallel lines intersect two transversals, so here we go, three parallel lines, 1, 2, 3 parallel lines intersecting two transversals. Then they divide the transversals proportionally. So these are going to be broken up just like the triangles will be broken up. So we get all of these lines are breaking up those sides proportionally, and it makes us have these here. We've got BC over CD, that's the right-hand side. And then we get AF over FE. So the parallel lines are going to break up these transversals proportionally. Now, because we don't have a triangle, we needed a third line because otherwise we wouldn't have two sections. Like if you took away that top line there, we wouldn't know how long the top AF and BC are. So we needed that third line to be able to make these proportions because in a triangle, they all come to like a stopping point at that vertex. Well, we don't have that vertex anymore since they're not meeting. So now we have to break them up. So 3 lines, we get these same proportions breaking them up. So again, it's working, just not in a triangle here. It's in just with 2 transversals. Okay, if A is equal to 2 and B is equal to 3, C is equal to 5, they want us to figure out what D is. Take it, Amber.
I do 2 over 3 equals 5 over x. And then, hold on. Then you get 15 equals 2x. And then 15 divided by 2.
She was getting there. All right, so let's do another one. If A, we're going to do, so that's all the first scenario. Here's a separate scenario then. If A is equal to 4 and B is equal to 8, C is equal to 5, then C plus D. So remember at the end, we're going to have to do C plus D. But what do we need to figure out first? We need to figure out what D is, and then we can add them together. Colette.
So you do 4 over 8, and then you could simplify that to half is equal to 5 over x. And then you cross multiply and you get 10. So then that's D, and then you add the 2 together and then you get 15.
Good. Now that we know what D is, C plus D would be 10 plus 5, or 15. Okay, just a couple. All right, so here's one involving angles and rays. If a ray bisects an angle, be very careful because I've noticed a lot of you have talked about bisecting sides. This is bisecting an angle, which means that if you look down here, this ray is bisecting, let me switch colors here. This ray is bisecting this angle C, and it's splitting it into 2 congruent angles. It is an angle bisector, not a side bisector. I see a lot of times people are taking the sides when it says it's an angle bisector. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides.
Okay, well, didn't the angle bisector theorem say that like A and B and D and B would be perpendicular? I mean, not perpendicular, congruent.
You're talking about perpendicular bisectors.
Oh, okay.
So we can't look at an angle bisector. Hold on one second. So we dealt with perpendicular bisectors before and what that means. And like we dealt with where these meet up and stuff. But this is kind of a new scenario just saying, well, when a ray bisects an angle, well, that angle is definitely bisected right there. I see it split into two congruent pieces. Then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So what we get here is that it hits that side and makes this a proportion with that. If you look at it, I'm going to flip this around for just a moment here. That's the bottom of the right triangle over the bottom of the left triangle. Can we see that? Like it's bottom over bottom. Like you see what I mean is when I look at the triangle like this, it's bottom over bottom. Like that there's still, that ray broke it up into two congruent, not two congruent triangles. It broke it up into two triangles. And when we set up these proportions, it's going to be bottom over bottom. So we've got bottom over bottom. And now, because this ray here going down the middle, we're going to use like this side over here. We also will have that this side, CA, that's there, will be proportional to CB. That's kind of like, I'm going to turn it around again so we can see it. It's kind of like the outside of the right triangle over the outside of the left triangle. Now, I didn't do right over right because if you notice, that wouldn't make them similar there because that's like, this piece is the one that's congruent to itself, remember, because of the reflexive property. So it doesn't make sense that that piece would be over the left or the right-hand side. It's got to be the one on the outside over the one on the outside. So we get CA over CB. So we have these as well, that they break them up. We're going to see, I think, an example in the next slide. You want to do this one, Colette?
So, you'd start off with 12 over 24.
Okay, let me get there in a second. First we have to acknowledge that there is an angle bisector right here. What she's about to do only works because there's an angle bisector right there. So, I'm sorry, I cut you off. Do it again now.
So, after you identify the angle bisector, then you go to 12 over 24.
2 over 24?
12.
12 over 24.
And then you could simplify that into half.
Okay, so that's going to become 1/2.
And then you want to find like the other piece of the thing since you're trying to find the thing. And so it becomes 10 over x.
That little piece is x?
Like, sorry, 10 over y.
Okay, so let's talk about that for a second here. I'll come back. I'm going to flip this over here. Let's look at that. If this piece right here, right there, is 10, how long is the other piece? 10 plus x? X minus 10. Because if you think about it, look, the whole length of this line is x. That's how long that whole line is. If you take away the 10, you'll be left with whatever is there. So we have to be very careful. This is a real tricky one there. That piece is x minus 10.
If you did y and then plugged it in,
You're gonna have a mess because you'll have two variables in there. Like you're gonna end up with two variables in there. Like if you had y, you'd have 10 over y, but then you're asked to find x. So I see what you're saying. So maybe you could solve it for y and then plug it back in and add it together. Yeah, I guess you could do that.
okay.
I mean, it's extra steps,
Yeah,
but if you're stuck, why not? She's saying instead of using x minus 10, could I use y and just set up the proportions like the last one and then add it to 10 at the end? Sure, we could do that. But let's finish it this way right here.
So then, it would be, so then you cross, so then it'd be half is equal to 10 over x plus 10. And then if the x minus 10 is equal to 20. And then you'd add 10. And
So in which case, we know that the whole thing is 10, and I'm sorry, the whole thing is 30, that x is equal to 30. What if I asked you how long this piece was right here?
that would be 20.
It would be 20. You take the whole x and subtract away the 10 that we already know, then it would be 20.
Like on a test or quiz, what would you call that if there's no variable there?
Well, I'd have to give you some letters or something. Like there, I could, like if I gave you some other letter for it, like let's say in on a test, it might look like this. I might ask you for how long is DC. You would need that information. I'm just asking you extra questions here that like what would you do in that scenario? Yes, ma'am.
When I first did it, I found the other piece and then I added 10 and I got.
That's what she was saying there. So the other way we could have done this was, like you said this, you've got 12 over 24 is equal to 10 over, now I'm going to call this y, a new variable, in which case we could still reduce and we would get 1/2 is equal to 10 over y, and we would get y is equal to 20, which is this piece right there is 20, and you could add them together and go backwards as well. Both ways are ways you could do it. Okay, that is it for today. I will hand your quizzes back to you. So if you actually hang on that, let me see if I got to just check next door and see if I'm good to hand them back. But at least you can get started on the homework in the meantime.